Okay, we are moving on to our next segment, which is another type of stoichiometry. We haven't done true gas stoichiometry yet because that's still a reaction type. We don't have any chemical reactions up here yet, okay? But what happens is if you're reading these questions, you'll see how many liters of a gas are found in a mole of that gas. And that's what this composition stoichiometry is right here. Very much similar to what we did in Chapter 3, just taking moles of a substance and converting it to grams, or grams to moles, just a simple three-step problem. Gas stoichiometry, on the other hand, is reaction types, where you have a chemical reaction where you're actually taking maybe grams of a solid and converting it to volumes of a gas. Okay? You haven't been taught that yet. Okay? But this up here in the purple, okay, when these are measured at STP, you can make certain presumptions. Well, you would, because we know what the pressure is, the 1 atmosphere, and then the temperature is 273. And then this is also a constant, okay? 9.8 is a constant. 3.14 is a constant. I'm sure there's others that in math class that you probably dealt with that maybe you could probably enlighten me on that as well. But those are the first two that come to mind. And when gases are measured at STP, you can also presume that the volume of that gas is 22.4 liters. Okay? And this is where all these numbers are coming from. In other words, it's what we call the ideal gas law. Okay? So pressure times volume equals N, or the number of moles, times this constant times a temperature. Okay? So like last chapter, you had Boyle's law, Charles's law, and the combined gas law. Here, you could say it's very similar to that of the combined gas law, but here you're also dealing with masses of a gas when you're given a temperature or that of a pressure as well, converting it to a mass. So this constant of 0.0821, which is right here, obviously, okay, we know that what's the pressure of a gas if it's at STP? 1. What's the volume of a gas if it's at STP? 22.4, okay? And then we presume that it's just 1 mole. I guess I'm not putting labels in there, so I won't do for this either. And then what is the temperature of a gas at STP? 273, and then that leaves this R constant. Okay? So what we see happening here is the only way to get R by itself is to do what on that side of the equation? Divide by 273. You're just using your algebraic skills, correct? 1 times 22.4 just gives you 22.4. 1 times 273 just gives you 273. So if we take 22.4, divide that by 273, that equals R then. And no surprise, when you divide them out, you get 0.0821. That's where that number comes from when these gases are measured at STP. Okay? You can make those presumptions because one of the things that will happen is you are going to have to use this ideal gas law if it's not measured at STP. But there's certain presumptions that we can utilize when it is measured at STP. Okay, now there's 2 ways you can do this. Dimensional analysis. Okay? That means that is dimensional analysis, if you remember that. Okay? Okay? Or you can use the ideal gas law every time. But you need to decide Am I just going to use dimensional analysis only, or am I going to use both the ideal gas law and dimensional analysis? You need to make that type of presumption. In other words, it's like trying to solve for volume in the combined gas law, where on one side you've got it in milliliters and on the other side you've got it in liters. As long as they're the same, you can solve for that. But if you have 1.8 on one side and 1800 on the other, it's just not going to equal each other out because they're not the same units. One's in liters, one's in milliliters. Maybe you just want to use what you think would be the simplest. Okay? In my estimation, I say dimensional analysis. This is why. Okay? Okay, it says how many liters of hydrogen sulfide are found in 0.18 moles of the substance at STP. So, you have the variable N, and you're trying to find the variable V because it's measured in liters. But since it's measured at STP, okay, we can make some presumptions. There's only one place to start, 0.18 mole, okay, and hydrogen sulfide would be what, do you think? H, and what's sulfide? That'd be sulfate. No. No. Just S. Okay? The charge of sulfur. Hydrogen. Does that add up to 0? H2S. Okay? Although you're not looking for a mass in this substance, but if you were, you would have to have this formula correct. In the bottom one, you're looking for a mass. So this idea of writing out formulas is not done yet. Okay, so how do you think you could cancel that mole out in your next step? What would have to go on the bottom? Moles. And since it's measured at STP, we know how many liters that is since it's measured at STP. 22.4. So these have canceled then. You're in liters of H2S, and what are we asking for? You're asking for liters. Two-step problem, you're done. Okay. So you take 0.18 times 22.4, and then that would give you your volume then. Okay. Now, that's not to say you can still use the ideal gas law if you wanted to. It's just a little more work. It's kind of like, for some reason, I'm trying to think of what it is in Algebra 2. The quadratic equation always works. Is that when you're factoring? Does that sound right? It's some mathematical process where you can take a shortcut or you can use the quadratic equation because that always works. This is something very similar. You can say we can take a shortcut with this dimensional analysis, or you can use the ideal gas law because that will always work. It's just a little more work, that's all. Okay? And you might not know what to ask. N is the number of moles. So in other words, what you're doing then, okay, you've got, if you wanted to use the ideal gas law, pressure equals 1 atmosphere, volume, your question mark, okay? What you might say, well, we know what the volume is, it's 22.4 liters. No, that's just a conversion factor. That is not your unknown. Okay? N is 1, R is 0.08821, and then temperature is 273. Okay?
Is it always
Oops.
0.0821?
Yes.
Or only when it's same temperature?
It's always 0.0821. There. So you can use the ideal gas law, but then this, to me, this is just a little less work that's going to give you the same answer. Okay. Because one of the things that will happen later on in this chapter, you will be solving for one of these in this gases where it's not measured at STP, where you would have to use the ideal gas law. Okay? And again, if I was sitting on that table, I have no idea what to ask. But give it time and a little more practice, and the more practice you get, the better you'll be at it. At least I believe so. Okay. The main thing to remember is that if it's measured at STP, you can utilize 22.4 liters. And utilize that as a conversion factor. Okay. So did someone calculate that out? Liters of H2S. Okay? Questions on this top one? Okay. Let's move on to the bottom. How many grams of nitrogen at STP? I worded that very well, did I? How many grams of nitrogen at STP are there if you have 13.15 liters of the gas? Okay. If you have 13.15 liters. Okay. I was trying to do this, trying to do two things at once, listen to the game and keep an eye on last class period and then do this at the same time. Not making excuses, but that's what happened. But anyway, you can use the ideal gas law, or you can use dimensional analysis for this. You can use that moles as a conversion factor, but notice we're solving for a mass of a gas. Okay, so in this case, the only place to start is with what? 13.15. Don't just do this, because if I was a betting man or a betting man, you're going to make a mistake. You're going to forget something. Okay? So it's measured at STP. What conversion can we utilize to cancel out that liter? Right? So liters. And don't just do that either. Okay? It's diatomic, but how many liters are there? 22.4. So once you do this, what is your conversion factor at STP when it comes to 22.4 liters gives you one what? 1 mole of the substance. And once you get it to this step, can you go from moles of N2 to a mass of N2? Yes, you can. Okay? If you don't carry that 2 there, chances are you're going to put what there instead? You're going to put 14.01 instead of these are now gone. You're in grams of nitrogen, and that's what we're looking for. Okay?
Do that with the first way.
The ideal gas law?
Yeah.
Okay? So what you would do then, okay?
Could you just take the atomic mass of N instead of writing 1?
Well, and then okay, and then, whoops, I did that wrong. So then you're going to solve for N, okay? And then once you get it into moles,
Multiply by the
then you multiply it by the atomic mass. Is what you're doing the same thing. It's just an extra added step. Where you, if you're doing a dimensional analysis, you do it all at once, and then you're done. So yes, again, the ideal gas law does work, but it is just that, a little more work, where dimensional analysis is much easier. Okay, okay, so 13.5 times 8.02 divided by 22.4, 16.45. Is that what you get? Yes, equals 16.45 grams of nitrogen. Okay?
We'll have to use the ideal gas law later.
Yes. Yep. That is correct.
I'll use it now just so I'm used to it.
Okay. There's nothing wrong with that. But even if you're using the ideal gas law, you still have that extra added step of dimensional analysis. But it's just one step instead of 2 or 3. We should not be in a rush to get left side. Can you speak for your classmate? Okay. Middle and right side. Okay. Barring no questions, that's all I've got. We'll practice some more of this tomorrow. All right. Catch up to you next time.